This material has been reproduced and communicated to you by or on behalf of the Australian National University in accordance with Section 113P of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further reproduction or communication of this material by you must be consistent with the provisions of the Act. Do not reproduce this material. Do not remove this notice.
There are a number of things you need to be aware. For example, if you have any questions, you can post on Watto. And also, when you write queries, keep in mind what should be the attributes you want to output, and what would be the logic, the syntactic errors, or whether it's semantically correct. Most importantly, make sure you follow the instructions carefully, because we will use some tool to do marking. So if you don't follow instruction carefully, you may lose some marks. Okay, we will try to give some partial marks during the marking if there are some partially, reasoning and partially answer there. Very important. Don't left your assignment submission to the last minute. Okay. Also, we want to arrange several drop-in sessions next week to help you assignment one. We will make the announcement in terms of time, day, and also the venue on Watto very soon. So just keep an eye on that. There is a survey for the first 4 weeks. It's available on Watto. We would appreciate if you could, take minutes to finish the survey and provide us feedback, so we can improve our teaching. Another thing is the census date. So it's approaching. Will be next Saturday. So it's a day you can decide to withdraw from the course without any penalties. Okay, let's get started. You may wonder why I put a picture there. So that little girl is a character in the book called The Foundations of Databases. So that's a very classic old book. It's all about the fundamental theory about a database. It was influential in terms of building the theoretical background. 5 years ago, when I was in Lisbon, attending some international conference, a group of database researchers get together. We had some birthday for this little girl. Basically, just people come from different places, different country, different university. We talk about what would be database research, the future, and how this is relating to application. So Alice has some question about a relational database. You have learned the relational data model in the last several weeks, right? So basically, it's just a table. You have columns, you have rows. So Alice has question, wonder, would this be very boring? Because we may have a lot of information, but in the end, we have to put this into table. It's flat. Some of friends of Alice also holding similar view. So they wonder, because if you watch the self-study video, you can see it's possible there will be some data independency problem, data redundancy problem, and update anomaly problem. So this kind of table-like structure potentially could have all sorts of problems. Particularly in real-life applications, it's quite often you have very complicated data requirements. Then that means when you update data, it's likely there could be some errors or other things. How can we handle that? And particularly if you want to have a database that could be running very fast. If you query, then quickly give you a result. How does database design relating to performance? So is that a bad choice with a relational data model? So that's what we are going to talk about today and also next week. How can we do a good database design to fix the problems? Let's start with something everyone knows. Spreadsheet. Everyone knows, right? We use this to record some information. Conceptually, you can see it looks like a table. You have columns, you have rows. So the question is, how does Excel spreadsheets different from tables in a relational database? So something we can think about is you learned a relational database, we could have constraints. We use constraints to ensure data integrity, but it would be difficult if you use like a spreadsheet to enforce some complicated, data integrity things. Also, SQL, your assignment, you write queries to find the information. So in this kind of structured way, database query is very hard to do on Excel spreadsheet. That's another difference. Of course, there are also other things in real-life applications. Relational database has been used everywhere, quite often in very large scale. For Excel spreadsheet, quite often it's convenient for individual, like we can have them in our computer. But in an enterprise environment, that's difficult to share information. There are also other things about security, transaction, recovery. Those we will talk about later on after the semester break. So, in order to understand how can we design a good database, the most important thing is we need to know what is a good relational database design, what is a bad relational database design. It's like two sides of one coin. That's what we are going to talk about. So you can see here, I have 5 parts to talk about today. Hopefully, we still have time to do this, because I'm really sorry the time we have spent on solve this issue. The first part is, why do we need function dependencies? Because we learn function dependencies, but why? Why we need that? Okay. Then we will go to second part. What is a function dependency? Then how can we find the function dependencies when you do database design? Then how function dependency can be really useful? Then finally, we will talk about some theory behind to support all this kind of how can we find, how can we use function dependencies. So that's the plan for today. Why do we need the function dependencies? So we talk about database design issue. Okay, but to understand database design issue, the question is, how do we know a database design is good or bad? If your manager asks you, say, okay, here we have a database, can you give me your opinion? Can you please tell me whether this the database design is good or bad, and in which sense? So think about so far what we have learned in this course. I think last week you learned conceptual modeling, ER modeling, or extended ER modeling. So the basic idea is in real life, when you have customers approach you or your manager asks you to do database design, you start with connecting requirements. You want to understand, okay, what I'm supposed to do with this database, what are the requirements? So to connect those requirements, a very good way is to have some conceptual modeling so you can share with your colleagues, your customers. So the starting point is conceptual modeling. Then from there, you can transfer a conceptual modeling into relational database schema. So the problem is here, because we are all different. Conceptual modeling is subjective. If we are given the same application scenario, the same data requirements, because we are different, So we may come up with very different solutions. So here are examples. So those three solutions, 3-year modeling, was from 3 different people, but for the same application, the same data requirement. They are so different. By the way, you can imagine tutors will be very difficult to do marking for your ER assignment, because each of you may have unique perspective and come up with different solutions. So that means with all sorts of different solutions, what kind of common issues we could find? Typically, there are 3 kinds of database design issues: inconsistency, redundancy, and update anomalies. So here is a quick summary for the material you saw in the self-study video. For data inconsistency, here we can see, for example, Tom. Tom, the same student, has 2 different birthdays. Or for a database Comp 2400, the same course, it has 2 different units. Or 2 different students, they shouldn't have the same student ID. So those are issues we call data inconsistency. The second kind of issue is about data redundancy. You can see here Tom's information, student ID, is stored twice in this table. And also course information, semester and unit, also has been stored multiple times. So this is a very small, simplified example. In a real-world application, you may have a table with all sorts of redundant information. The last one, So the last type of database design issue is update anomalies. We can see here, suppose we have this table here. If we only want to insert a new database, a new course into this table, into the database, but we don't know. We don't know which student has enrolled this course yet. We just want to add the information about the course only. We would have a problem, because we cannot really just enter half of the record if the primary key is defined on both student ID, course number, and also the other attributes if we, like semester. Okay, so we will have a problem even we want to enter some information, but we cannot do that. And also, if we want to delete some information, for example, Comp 2400, we want to delete the enrollment information of a particular student, but want to keep the information about the course. We could also have a problem if that record is the only record has that course information. Similarly, if we want to change the date of birth of Michael, in this case, Michael has several records. If it happens, we only change one of them, forgot another one, then we will have a data inconsistent issue. So those are the problems quite likely happen in the relational data model because we have a table. Like Alice said, it's flat, and that could have all sorts of issues. But we're going to fix this. The very simple and fundamental idea is we are going to properly decompose a table into multiple tables in a proper way to avoid this kind of database design issues. So that's what we are going to talk about this week and the next week. Okay, so that comes to several questions. How can we identify those database design issues? So can we just manually do this? Because you've already be aware of this kind of design issue. But when you have a database, should we just manually say, okay, this is an issue, but that won't be efficient. And also, how can we prevent this kind of issue from the very beginning, even when we just start to design a database? Because the cost will be much higher if we have a poorly designed database, then later on just try to fix the data issue. So the basic thing is we can design a database, a good database at the very beginning to stop this. Then another thing is any systematic way we can follow some guidelines? Otherwise, we have to rely on experience. So those are the things we will talk about. Okay, so functional dependencies. In my experience, quite often, function dependencies sounds very theoretical. Okay, so why do we need function dependencies? I think this is a question I have been often asked. So basically, function dependencies tell us something about a relation. It tells the relationship between and among different attributes. So then we can leverage this tool to have some, we say, formal way, or you could think this just a systematic way to assess whether a database design is good or bad. Or if you have several database solutions, you can use this to compare which one is good or bad in which aspect. So this is related to how we justify the goodness and badness of a database design. In practice, sometimes people doing this top-down, and also it's also possible you're doing bottom-up. But top-down is a typical approach. It's more popular in practice. So that's what we are going to talk about next week. It's called normalization. Now, what are function dependencies? So function dependencies, informally, we say, okay, if we have some functional dependency defined on a relation, it basically tells us some attributes in this relation, the value of that can decide the value of some other attributes. That's the informal definition. Like here, if we know kangaroo, this value, whether kangaroo can fly, no. Whether kiwi can fly, no. So basically just the value of some columns determines some values of other columns. That's it. But why it called functional dependencies? What does functional mean? So functional dependency basically is very much similar to function. But here I'm talking about a total function. So if we have a function, we basically have two sets of elements. Then a function just maps the elements of one side to elements of another side. Okay? Like here, we have some elements of different shapes that map to some dots in the core domain. So that's the basic definition for function. So before we look into how this is relating to functional dependencies, let's do some simple exercise. So here we have 4 cases. Which cases are total functions? Can someone tell me? Top right? You think is that a total function? Is it? Yeah. Which one are total function? How about the first one? Good. Yes. So here, in this case, we have the bottom ones. They are total functions, because every element in the domain is mapped to something in the core domain. And also, every two different elements in the domain, or every element in a domain only mapped to one element in the core domain. Okay? Then, how does this relate into functional dependencies? You can see here now, we have x determines y. Okay? We call x determinate, y dependent. So it's kind of similar to domain and the core domain. We can have a look into some example. This is just some random function we pick. Okay? So you can see here, if we have x, the output x squared. Then you can think about x just from one set, then that determines the output. Okay? Any question for this? Okay, good. We move on. So with this in mind, let's have a look into the formal definition. So there are two sides, how we present a functional dependency. So the syntactic expression, basically just x determines y. Okay, x is determinate, y is dependent. Semantically, we say for a relational database, for any relation with a function dependency x determines y, any two tuples in the relation, if they have the same value for x, then they should have the same value for y. One thing tricky is this definition didn't talk about anything about the two tuples if they have different value in x, right? They only said that if they have the same value on x, then they must have the same value for y. But if they have different value for x, what would happen? Doesn't matter, exactly, because this function dependency doesn't care about that case. So it means you can have the same value, different value, that's all good. A function dependency is trivial if y is a subset of x. Let's do some simple exercise. If we have a relation schema, okay, A, B, C, D, E, F, G, H, we have a function dependency, B, C, D determines G, okay? So we can see x will be B, C, D, and G will be, y will be G. If we have two tuples in this table, can we say this table violate or not violate this function dependency? Violate, right? Yes, because G1 not equals to G2. By the definition of function dependency, if all values for B, C, D are the same, then they must have the same value for G. So here, this is not the case. If we change this to G1 for both tuples, and also assume other part of table is fine, then this function dependency we can say is satisfied. Okay? So function dependency is a constraint. So that requires all relations over a relation schema need to respect this constraint all the times. Let's consider another example. This is a small table. So how about ABC determines AB? Valid or not valid? No, right? Yeah, because it's a trivial function dependency. Because AB is a subset of A, B, C, so that it always satisfied. How about A, B, C determines D? Yes, very good. Second and third together actually violate this function dependency. Yes. How about another one? E determines A, B, C, D. Because E has different values, because function dependency only care about tuples. If they are same, they should have same value. If they are different, then always satisfied, right? Okay. Now the question is, how can we identify function dependencies? So it sounds function dependency could be useful, but where we can find it? Typically, there are two ways to identify function dependencies. One way is through data. This could happen, for example, if you have a job, then your manager said, okay, can you please design a database? But we don't have any information about like documents. We only have all the database, the data, that's what we need to manage. So that means you could only look into data, try to figure out what kind of function dependencies you need. In that case, analyze data would be important. The second case would be better. If you have customers, you can talk to your customers. They can tell you, okay, what kind of data requirements we need. We want to build this into a database. So that's, in that way, you can develop some function dependencies. We can have a look into this case. So if we only have some sample data, then we try to get a little bit idea about what kind of functional dependency could be useful. So we may, based on sense, say, okay, student ID determines name and the date of birth. Sounds reasonable, and also the data, or tuples, if they have the same student ID, they must have the same name and the date of birth, right? Similarly, we may find course number determines unit. For example, Comp 2400 is a 6 unit. This just sounds like a common knowledge, and that can be also checked through this sample data. Or we may have student ID, course number, and the semester that determines name, date of birth, and the unit. So one important thing is when we talk about a key is always a function dependency. In the sense, the X is the key attributes, the Y would be all attributes in a relation schema. However, the problem with sample data is we may also get some wrong information. If only based on this table, we may get a conclusion, say, okay, name determines student ID, or date of birth determines student ID, but that doesn't really make sense, right? So that means even sample data could be useful, could help us find some useful information about a database, the data requirement, find some functional dependencies, but we also need to be mindful whether those function dependencies have really captured the requirement in the real-world applications. Then the second case is we can identify function dependencies based on data requirements. So here is a simple example. Suppose we have some data requirements, R1, R2, R3, R4. Okay, this suppose are given by your customers. Okay, so okay, that's what I expected. That's what I want, to be built into a database. So let's look into this. For R1, a guest can make several bookings in a hotel for different dates. What kind of function dependency we could have for this? Yes, so there's nothing we can get for function dependencies. Because function dependency is kind of constrained, but it cannot capture everything. So in this case, this kind of data requirement, function dependency cannot capture. How about the second one? A guest cannot book 2 or more rooms in the same hotel for the same day. Yes. This is a function dependency we could have. Why? We can have some example. For example, if we have this function dependency, if a table intended to have same guest, same hotel, same date, but a different room, that will violate this function dependency. So by enforced function dependencies like this kind of requirement can be achieved. Okay? Any questions? Okay, let's move on to the next one. A guest can make 2 or more bookings in different hotels for the same day. Any functional dependency we can get from this requirement? It's difficult, right? Yeah, so someone shake her head. Yes, no. So the last one, a room in any hotel can only be booked by one guest on the same date. So it means just no double booking. Very good. So similarly, if we check here, so for example, this kind of situation can be avoided if we have this function dependency. Okay. So let's stop here. Let's have a break, because we have gone part A, B, C. We have another 2 parts. How can we use functional dependencies and also the theory? So let's have a break. We come back, how about 2 o'clock? right, let's get start again. How to use the function dependencies. Today we are going to talk about how can we use the function dependencies to find the keys. Next week, we are going to talk about how can we use the function dependencies to break table into smaller table to avoid the design issue like inconsistency, redundancy, or update anomalies. So that will be next week. But today we are going to talk about, okay, how can we use that for identify keys? Oh, sorry, what happened? Sorry, I don't know what happened. I didn't touch the computer, just maybe just bear with me 1 second. I grab the technician, help me solve this. That's all right. Nobody there, so I try again. Maybe better. Okay. So in the video, you have seen several different kinds of keys. So for example, super key. What is a super key? The idea is very simple. A super key can determine all other attributes in a relation schema. Okay. Then there is another concept we call candidate key, or simply just call key. A candidate key is a super key, but it's minimum. Minimum in the sense, if we remove any attribute from a candidate key, then the left ones cannot determine the other attributes. Okay. There is also a concept called primary key. Primary key is a candidate key. So in terms of the name, candidate key just means they are candidate for primary key. So this picture summarizes the relationship between those different notions of keys. Okay. So the question is, if we have a set of function dependencies, how can we find keys, candidate keys? Because if we can find the candidate keys, then we can select one as a primary key. There is some algorithm, but this algorithm based on the fact. What is a key? The main property is when we talk about a key for a relation schema, it means the attributes of the key together can determine all other attributes. So based on this idea, we have a set of function dependencies as input. Then the algorithm will give you a set of keys on relation schema. There are several simple steps. The first step is to compute the closure of X. So X here just means a subset of attributes of a relation schema. What does closure mean? Closure just means the closure of X means it's a set of attributes that depend on X. So any function, any attributes depend on X, we put that into the closure of X. So this algorithm calculates the closure of subsets of attributes. If closure contains all attributes, then that meets the condition to be a super key, but not necessarily a key. Because key has another condition, it needs to be minimal. This is why the third step said, okay, we still need to check whether that's minimal, means whether we can remove any attributes from the closure, then still be a key. Okay, so that's a general algorithm. We will do some exercise. There's a notion called the prime attribute. So prime attribute just means if a relation schema, we have attributes. If attribute appear in at least one key, then that attribute is called a prime attribute. If this attribute doesn't appear in any key, that's non-prime attribute. Why we need this? You will find out next week, because when we want to do normalization, in other words, when we want to break a table into several tables in a proper way, we need this notion, prime attribute, in the algorithm. Sorry, I don't know. I'm really sorry about that. I don't know what happened. I will figure out after the lecture, have a double check. So let's do some exercise together. If we have a relation schema, A, B, C, D, E, we have 3 functional dependencies defined on this relation schema. Then if the question is ask you to find all the candidate keys and also super keys, how would you get started? Because candidate keys needs to be minimal. So a good starting point is to look into subsets which are small, from smaller ones to bigger ones. So that means we can do some calculation from the single attribute. For example, A, what's the closure of A? What's the closure of B? What's the closure of C? What's the closure of D? Okay. If the closure of A contains all the attributes, that will be make A to be a key, but in this case, the closure of A just AC, doesn't include all the attributes. So once you check all single attributes, then you can decide whether you move to 2 attributes, 3 attributes. This may seem a little bit tedious, but here is more about the principle, because in general, you can write code to do this very fast. Okay, so here we can see in this example, when we tried a single attribute and also 2 attributes, none of them give us all the attributes in the relation in the closure. But when we move to A, B, D, that gives all attributes. Can you see how we get the closure of A, B, D? So the idea is if we have ABD, we want to calculate the closure of ABD. The first instance, just put ABD into the closure, right? Because it's definitely determines itself. Then you can look, you can check the function dependencies. If A determines C by itself, the ABD should also determine C. So you just add C in. Okay. Then you have C and D. By another function dependency, C, D together can determine E. So you have everything. Okay. So start with itself, all the attributes in itself. Then scan through all the function dependencies. Then whenever you have some x, like you have already included x, then you add a y into the closure. We will talk about more later on. So in this case, if ABD is a candidate key and actually is the only candidate key, then we can easily get the super key, because super key just means just include all the candidate keys plus any other attributes which has more attributes on top of that. So in this case, ABD, ABDC, ABDE, and ABCDE are all super keys. If we look back, the previous example, we talk about we have 4 data requirements that give us 2 function dependencies. So in this case, we can use these function dependencies to determine the primary key of the relation booking. Because how can we choose primary key? We can just base on function dependencies. In this case, we can have 2 options. As a guest number, hotel number, date. This could be a primary key. Or a hotel number, date, a room number. That could be. Either of them is fine. They're all called candidate keys. Okay, so this shows how we use function dependencies to find the keys. Then from there, you can choose primary key. So for example, if we say we remove the requirement, R1 and R3, but we have a new requirement. A guest is not allowed to make more than 1 booking for the same day, even in different hotels. So for this new requirement, can we find some functional dependency? I show you, we can. Okay, we can have a guest number and the date together to determine hotel number and the room number. So by that, because we replace R2 and R3 by R5, that means we now have 2 function dependencies. So you can see the purpose here is once you have different requirements, you have different function dependencies, then the primary key actually different this time. Okay, you could choose the guest number and the date as the primary key. Okay. Any questions for this? Okay. Now we come to the theoretical part. In the past years, some students feel this the topic, on function dependencies and the normalization a bit challenge. My opinion and also my experience is it might look like that. At the beginning, just sounds a lot of symbols. But if you could get the intuition behind, then you feel everything is straightforward. So let's look into this theorem, because those are the things to support all what we talk about. How can we use function dependencies? There are some beautiful theory behind. Let's start with inference. Why do we need the inference? Because we could get some function dependencies from data requirement, but that cannot capture all possible function dependencies. This is a typical example. Suppose we have 2 function dependencies. Student ID determines project number, and the project number determines supervisor. Because the meaning just means, okay, each student work on 1 project. Okay, so we know, once we know student, then must be the same project. Then each project has 1 supervisor, so those requirements can be captured by the first 2 function dependencies. Then for the function dependent student ID determines supervisor, we may not capture it, but that can be inferred from the first 2 function dependencies. Okay, so this is what we talk about, the inferred function dependency, because we may have a set of function dependencies, but there are some other function dependencies that are also correct. They can be inferred from the set we have. But how can we know that? To do that, the thing is we need to find a systematic way to find all inferred function dependencies. That means we need some rules to help us. The rules basically just means if we have some function dependencies, they are true. Whenever those function dependencies hold on a relation schema, then by applying those rules, we can get other function dependencies. They must also be true. So that's the meaning of inference rules. There is a beautiful theory called Armstrong theory. It basically covers 3 simple inference rules. The first one, reflexive rule. So if we have x and y, of course, we can say a subset of x and y, that's y, depend on x, y, reflexive. The second is the augmentation rule. It means if we have x determines y, then we can add another set of attributes, z, into the both sides. Okay? Transitive rule means x determines y, y determines z, then x determines z. So we just use this notation to indicate a set of function dependencies can infer some other function dependencies. Let's go through these rules one by one. The first rule, reflexive rule. You can see here, if we have student ID, course number, semester, of course, it determines course number and semester, right? So X, you can consider that's a student ID. Then Y, just course number and the semester. It's straightforward. But this rule is important in the proof, because when you have several rules, you want to derive something, even some rule simple like this, that's important. The second rule, augmentation rule. In this example, if we know course number determines unit, if we know this function dependency determines another function dependency, because we can add the semester, this attribute, into both sides. So that means course number semester determines unit semester. Okay, so X is course number, Y is unit, Z is semester. Okay? Any questions? Okay. Okay, the third rule, transitive rule. So if we know student ID course number determines course number, we also know course number determines unit. We can translate this into student ID course number determines unit. So it's transitive. Okay, X is student ID course number, and Y is course number, Z is unit. They are all very intuitive, right? That's good. So from these 3 basic rules, some other additional rule can be derived from these 3 basic rules. For example, we may have a union rule. If X determines Y, X determines Z, then we say X determines Y and Z. Okay, this rule can be derived from the previous 3 rules. In this example, student ID determines name, student ID determines date of birth. Of course, student ID determines name and date of birth. Or we could have, decomposition rule. If X determines YZ, okay, then we may split Y and Z. That means we have X determines Y and X determines Z. Okay, the same example, student determines a name and date of birth, then we split name and date of birth, then we have 2 functional dependencies. Still very simple, right? So if we're back to the previous example, apply a transitive rule on those two function dependency, student ID determines project number determines supervisor, we can easily get student ID determines supervisor. It means in terms of project, if we know student ID, then we know what would be the associate supervisor for this student. It's just based on transitive rule, we can prove the correctness of this. Let's do some exercise, okay? So can we see this correct? Yes, okay, that's just augmentation rule. We can add some attributes to the both sides. Is this correct if we shift the things around? Not correct. So here is some counterexample. You can see here, if we have xz, a and c together, determines b and c, but we cannot really, like those two tuples, we can really claim x determines y. Okay, so this, we cannot reverse this rule. How about x determines y? Whether we can say y determines. Good. Okay, so this is also another example. So it means the function dependency is just one direction. Okay, we cannot reverse that. So here a little bit too theoretical, but don't worry, you are not required to understand things behind, but just give you a general picture. So in theory, we often talk about soundness and completeness. Okay, so soundness just means when we say we have these rules, they're so simple, right? So can we really claim we can derive all implied function dependencies just by those simple rules? I mean, soundness just means that all the things derived was correct. Whether those rules can always give us correct result. So if we can, then we say this is sound. Then completeness is another direction said, okay, can we derive all implied function dependency just by this simple rule? So if we could, that's complete. So it's really nice if we can claim something, like this is set of rules, they are both sound and complete. So fortunately, Armstrong rules has been proved. It's sound and complete. So if we look into picture here, quite often we start with some function dependencies. By applying Armstrong inference rule, we can expand it. Because the inference rule just tells us all other function dependencies implied, and they are all correct. So you can see here, if we have sigma, a set of function dependencies, by applying Armstrong rules, we get a natural set of functional dependencies, all implied function dependencies. So the question is, okay, sounds great, because those rules are so simple. Can we just use those rules to find all, to compute, just like to find all implied function dependencies? In principle, yes, we can, but it's not efficient. Okay, because of course it can, because it's sound and complete. However, when we talk about efficiency, how easy we can use this rule to get all implied function dependencies, that's different. That's not efficient. This is one example. For example, we have a relation schema ABCDE. Then we also have some functional dependencies. If we are asked to answer the question, okay, whether DB determines A is implied by sigma, that's difficult because we have to think about, okay, how can we prove that? Because in the end, we want to get this conclusion, DB determines A, or to show this is impossible. So to to derive this conclusion, whether DB determines A is implied or not, we have to construct some proof. Like here, this is a proof to show it is implied. But you can see the proof here start with DB determines B. It's reflexive, right? It's easy because DB, of course, determines B. Then we know B determines E. This is given in the sigma. That's a given condition. So we put them together. We can use a transitive rule, get DB determines E. Okay, DB determines E, but we want DB determines A. So we have to think about how can we go further. Then we can use augmentation rule. If we add DB to the both sides, we get DB determines DBE, right? Then we want to get rid of DBE. So then we say, okay, DBE determines DE by reflexive rule. Then we get DB determines DE. Then we use DE determines A. That's a given function dependency. Finally, we get the conclusion DB determines A. But this would be a worry if I give you a assignment or final exam and say, okay, prove this. If you couldn't find it, you would wonder whether just I didn't find it or whether I can really say, conclude, it's just not implied. So it's not really practical. In theory, it's beautiful, but in practice, it's not efficient. Okay, so this is why we talk about some algorithm, very efficient algorithm to do this. The idea is if we have a set of function dependencies, then we want to decide whether X determines Y is implied by this set of function dependencies. We can simply just calculate the closure of X. Because we talk about the closure of X just contains all attributes depend on X. Okay, once we have a closure, then we can easily conclude for any attributes in the closure, if they are Y, they appear in Y, of course, then X determines Y. Then we can easily just get the conclusion. If you look into the algorithm itself, we start with X. We put all the attributes in X into the closure. Then we scan each function dependency in sigma. If their determinate X prime appear in the closure, then we just add the dependent of that function dependency into the closure. We just do this one by one for each function dependencies, then go another round until there's no change anymore. So it's like we start with X, we expand. In the end, we have a closure. Let's look into some example because the intuition is very simple. So here, if we have A, B, C, D, E, we have some function dependencies. If we have two questions to answer, the first one, AD determines CE, whether hold or not. Like I said before, we calculate the closure of AD. To calculate closure, we first just add AD into the closure. Then, because AD determines C, we add the C. Because A determines C, then we add the C. Okay? Then we have ADC. That's a closure. Then because C and D together determines E, then we can add the E. We do again, we cannot go further. Then we get the closure of AD, that's ADCE. Then we just check. We check the question, the CE, whether it's a subset of closure. If it is, in this case, then we conclude, okay, this set of function dependencies implies this function AD determines CE. Okay? So it's fairly easy. The same for the second one. We calculate a BD. We first put a BD into the closure. Because B determines C, we put a C as well. Because CD determines E, we put a E. Finally, we have BDCE, that's the closure. Then we compare with the question, the Y in the question, that's AC. Because AC is not a subset of the closure, so the conclusion is this function dependency is not implied by the given set of function dependencies. Any questions? You can see this approach much easier than using Armstrong inference rules, right? You can quickly just go through function dependencies. Sometimes you may have to go to the second round. First round, you add all the things into closure. But sometimes when you go second round, you could add more. But very soon, you will reach the fixed point. Then that's the closure. OK, then that means if we have two function dependencies, they may look different, OK? But semantically, they imply the same set of function dependencies. What does this mean is, OK, you may look, OK, this set of function dependencies may be 3, another set of function dependencies may be 10. But it potentially could be, they are equivalent. They're just exactly the same semantically. This is one example. If we have x determines y, y determines z, that's one set of function dependency. Another set is x determines y, y determines z, and x determines z. Sounds one more, one extra. But because we can derive the third one based on x determines y, y determines z, so they look different, but in terms of their implied function dependencies, they are equivalent. I want to ask you some questions. If we have two sets of function dependencies, sigma 1 implies sigma 2, and also sigma 2 implies sigma 1, can we conclude they are equivalent? Yes. Second question, is that possible? We have two sets of function dependencies. They're different, but they have equivalent implied function dependencies. Yes, that's what we just talked about. How about we do another way around? Is that possible? Their implied function dependencies are different, but they are same. No? OK, good. That's all good. OK. We have something. I was planning to check if time allows, we can talk about a little bit. So that's about, you can see here, when we have a set of implied function dependencies, how can we find the minimum set of function dependencies which have equivalent, equivalent to other function dependencies, but it's minimal? Can we find the minimal set of function dependencies, but without losing any semantics? So this brings to minimal cover. In some sense, minimal cover is the hardest topic in this course. It could be, it's not, it's just very confusing, but it's needed for normalization next week. So here, because I will still talk about this next week, so here maybe just briefly, I talk about this just like when you watch the self-study video, then you get a little bit, intuition behind. So why we need minimal cover? You think about, function dependencies we talk about. When we talk about implied function dependencies, that means that's all the semantic information it captures. But if we don't look into minimal set of function dependencies, that means we could have redundant function dependencies, right? Redundant means some function dependencies not needed. And it could also mean some function dependencies, maybe we can remove some attributes from for example, fun x, but actually we still have the exact same semantic. So potentially, when we have a set of function dependencies, we don't know whether we have some redundancies in function dependencies. But why this is bad? Because when we later on talk about normalization, how can we break a table into multiple smaller tables? We rely on function dependencies. If the function dependencies we have is not minimal, that means the way we break a relation schema into several relation schemas, the way we break them down could be not minimal as well. Implicitly, we could have some redundant attributes spread over different relation schemas. So that's the reason why we need to look into minimal cover. So here I just give very brief steps for this algorithm, how we find the minimal cover for a given set of function dependencies. So basically, if we say sigma is the set of function dependencies you have, okay, then you may wonder whether it's minimal. How we do that, you just go through several steps here. First, you start with the given set of function dependencies. Then second, you consider the dependent of each function dependencies. What does this mean is that if dependent has more than one attribute, you separate them. So if you have a function dependency x determines a1, a2, ak, you just break this one functional dependency into multiple functional dependencies. So that could be x determines a1, that's one functional dependency, x determines a2, another functional dependency. Why do we need to do that? It's more like if we split them into small pieces, then later on we can easily find which small piece is redundant, we can throw away. If we don't do this, it could be, the bigger function dependency could be partially redundant, but we cannot throw them away because it's just partially redundant. If we throw it away, then we may lose some information. But if we try to put each function dependency minimal first, then that allows us to remove some function dependencies later on. So this is the first step. We do something about dependency. So separate each attribute in the dependency of each functional dependency. Then we look into X side. Okay, the basic idea is just check attributes in X, whether we can remove not unnecessary attributes. So this is a tedious part, because if we have X determines A, we want to say, okay, if B is the attribute in X, we want to say whether we remove B, then we won't lose anything. We need to check. If we would lose something, then we cannot remove it. But if we still have the same information, we still have the same set of implied function dependencies, then that means we can remove. You can imagine if X has 10 attributes, how difficult it is. We have to try each attribute, try to remove one attribute at a time. So that's quite a tedious process. So that's the basic idea. Then finally, we need to remove redundant functional dependency. So you can see this is the general idea of algorithm. We start with the given functional dependencies. Then the first step, we check the y side, split them. Then we check the x side, try to remove redundant attributes in x. Then the last step is to remove redundant functional dependencies from the set. I think I should leave the examples to next lecture because it could be a bit tedious at the moment. It's better we talk about next time when you're more on top of functional dependencies. So here I include some example with a lot of details in the lecture slides, so you can just have a look, then we discuss next week. So that's a lot, just because we need to check, do a lot of checking. But once you know the principle, it's not difficult, okay? So that's all for today. Apologies for the technical issue. I will talk to technicians. We try to figure out, and it won't happen next time. Thank you.